In this video, we're going to look at the graphs of the tangent function, the cotangent function, cosecant, and secant. I'm going to do two of them in this video. So we're going to talk about the graph of tangent and also the graph of cosecant. And I'm going to leave cotan and secant for you, but they will be done in the subsequent video. So the first thing we want to remember is that a function has a vertical asymptote when the denominator is 0 and the numerator is not 0. So for tan, the tan is equal to sine over cosine, and secant is 1 over cosine. So both of these functions are going to have vertical asymptotes when the denominator is 0. Okay, in both instances, the numerator is not 0 at the same points. So these are going to have vertical asymptotes when cos of x is equal to 0. Okay, so when does that happen? Well, it's all multiples of pi by 2. So it's pi by 2 and then plus k times pi. So where k is an integer. So you want, maybe I'll just draw a little picture here. So cosine is 0. It's going to be at pi by 2. So you want all angles that have terminal side the positive y-axis, but also at 3 pi by 2. So that's this terminal side. So you want all of those angles as well. So these two are pi apart. So if we add multiples of pi, we're going to get all of them. Okay, similarly, cotan is cos over sine, and cosecant is 1 over sine. So these guys are going to have vertical asymptotes when sine of x is 0, and that happens at all multiples of pi. So that's going to be k times pi for all integers k. So again, for this one, sine is 0 at pi, so terminal side over here, and also at 2 pi. So that's where the terminal side and the initial side are actually the same. Okay, so that's when the y value, where you're on your terminal side, is 0. So those are going to be where our asymptotes are. So if I wanted to graph tan of x, I know, and I'm going to make two steps. I know that I'm going to have a vertical asymptote when cosine is 0. So this is going to be at pi by 2, okay, or negative pi by 2, or 3 pi by 2, okay, or negative 3 pi by 2, okay, in this picture, and keep going. So we get all these vertical asymptotes. So then we want to think, okay, well, what happens in between them? So we'd want to think, where is tan of x 0? Okay, so remember that tan of x is sine of x over cos of x. So that means that tan of x is 0 exactly when the top is 0. So that's when sine of x is 0. So that's at all the multiples of pi. So it's k times pi, where k is an integer. Okay, so for instance, at 0, that's 0 times pi. Tan is going to be 0. Okay, so I have a point at 0, 0. I'm also going to have a point, so halfway between pi by 2 and 3 pi by 2 is pi. Okay, and here I'm going to have negative pi. I'm also going to have zeros there. Okay, so those are all the places where it's 0. Now in between pi 0 and pi by 2 is pi by 4, okay, or 45 degrees. And this is also a special angle, because if you remember, sine of pi by 4 is equal to cos of pi by 4. They're both root 2 over 2. Okay, so that means that tan of pi by 4 is actually 1. Okay, so here it's 1, so it's positive. Okay, I'm going to put 1 here. Okay, so we're going to have a point at 1. Now if I'm negative pi by 4, that's going to be in quadrant 4 because I'm going clockwise instead of counterclockwise. So if it's in quadrant 4, then the cos value is positive, but the sine value is negative. So they're equal, except one's negative, one's positive, so this is going to be negative 1. Okay. Now, in between negative pi by 2 and 0, there's no place where the function can switch from positive to negative. So that means in this interval, we have to be fully negative, which means that we're going to have to approach the asymptote down here. Okay, so what happens is you get, I did that a bit too steep here. Okay, so you approach, you approach like this. Okay, and then in the interval from 0 to pi by 2, I'm always positive. Okay, so then I'm always positive, and I have to approach the asymptote this way. Okay, and it turns out that that's what happens in all of these intervals. Okay, so at these, so this one is going to be 5 pi by 4, and this one's going to be, oh, sorry, I lied, 3 pi by 4, and this one's going to be 5 pi by 4. So those are going to be 1 or negative 1, okay, and it just repeats over and over again. Okay, so we just keep having the same graph like this. Okay, so that's what our graph of tan looks like. Now notice, I'm just going to switch colors here. So this is one period, or one cycle of our graph. And notice that it goes from negative pi by 2 to pi by 2. So that means that it has length of pi instead of 2 pi. Okay, so that's a little bit different from the sine and the cos. Okay, so now some properties of this graph. So the domain is everything except where the asymptotes are. So we cannot have x equal to pi by 2 or any integer multiple. Add k pi to that. Okay, the range, that's the y values, is all real numbers, or negative infinity to infinity, because the y values, we go to negative infinity all the way in between and then up to positive infinity. So every y value can be obtained. Okay, the vertical asymptote equations are the same as the domain except with equals. So we have everywhere, every x value that's not in the domain is a vertical asymptote. Okay, the y-intercept is when we cross the y-axis, that's at the point 0, 0. Okay, but there's many x-intercepts. So one of them is 0, 0 is an x-intercept, but they notice that they occur at multiples of pi. Okay, so the x-intercepts, there's infinitely many, and the x values are k times pi, and the y values are 0 always. And this is again for k an integer. So if k is 0, we get the point 0, 0. If k is 1, I get the point pi 0, which we can see in the graph up here. If k is negative 1, I get the negative pi 0 point. Okay, now tan is an odd function. So I think we talked about that earlier. Maybe you might not remember, but sine is an odd function and cosine is an even function. So tan of negative x is sine of negative x over cos of negative x. Sine of negative x is negative sine of x, and cos of negative x is just cos of x. So that's negative tan x. So that's why we get it's an odd function. So that means it's symmetric with respect to the origin. Okay, so you can see this part of the graph here is just rotated around the origin to be this part of the graph here. Okay, and that's the same for the entire graph. So this part, if we rotate it, is going to land right here. So it's symmetric about the origin. And like I mentioned up above, tan has period pi instead of 2 pi. So the graph repeats itself every pi interval. Maybe I should say, be more specific here. Repeats itself every interval of length pi. Okay. So I'm going to skip the graph of cotan. It's very similar to the graph of tan. So you want to think about where your vertical asymptotes would be and where your x-intercepts would be, and then the graph is going to look fairly similar. Okay, now let's talk about the graph of cosecant. So remember, cosecant is 1 over sine of x. Okay, so it's helpful to start with the graph of sine. Okay, so I'm going to draw the graph of sine in, let's do a really light color. So like, I wonder if yellow will show up. Maybe that's too light. Okay, let's try green. Okay, so we know that it goes up to 1, down to 0, down to -1, up to 0. Okay, and then I can keep going in this pattern. Okay, so this is the graph of sine x. Okay, now we want to graph cosecant x. So everywhere that sine of x is 0, we're going to have a vertical asymptote. So at all of these x-intercepts here, I actually get a vertical asymptote. Because I can't divide by 0. So I'm just going to replace all of these with vertical asymptotes, like that. Okay, so maybe I should say, so this is pi by 2, pi, 3 pi by 2, and 2 pi. Okay, this one is negative pi by 2, negative pi, negative 3 pi by 2, negative 2 pi, etc. Okay, so that means that this is x equals 0, x equals pi, x equals 2 pi, x equals negative pi, x equals negative 2 pi. So that's where our vertical asymptotes are. Okay, now for the, and oh yeah, we want to remember that this is 1 and -1. So if I wanted to graph cosecant, if I'm at pi by 2, so cosecant of pi by 2 is going to be 1 over sine of pi by 2. And sine of pi by 2 is 1. So this is 1 over 1, so this is 1. So actually, this point is on both graphs. Okay, similarly, cosecant of negative pi by 2 is 1 over sine negative pi by 2. And that one's -1. So this is 1 over -1, which is -1. So these points at 1 and -1 stay. So they are on the graph of cosecant. Okay, so there's some points to work with. Okay, now we just have to think this is our graph. Okay, so as I go from this point to 0, let's say, my y values are going from 1 to down to 0. Okay, so so that means that the bottom here is going from 1 to 0. So if I take 1 and I divide it by a number that's getting closer to 0, that's going to give me a bigger number. So it's actually going to it's going to approach the asymptote up here. Okay, so we know it approaches this asymptote, and it has to go either up or down. Okay, now I'm taking 1 and I'm dividing it by a positive number that's approaching 0. Okay, so that's why it has to go up. Similarly, on this side, it's doing the exact same thing. So it has to also go up on that side. Okay, so that's what it looks like in between 0 and pi. Okay, now if we do negative pi to 0, okay, so as I'm going from on this interval, okay, so here's my y value is -1, but in this interval it's bigger than -1, so it's a smaller number, but negative, so it's bigger. So I'm taking 1 and I'm dividing by a negative number that's approaching 0. So that's going to approach negative infinity. Okay, the same happens down here. So when the sine graph is below the x-axis, that means that the y values are negative, which means cosecant is going to be also negative. Okay, so similarly now it happens, it just repeats itself. So these ones go up, these ones go down. Okay, these ones also go down. Okay, so oops, and up here as well. This one goes up like that. So that is the graph. So the blue graph is cosecant of x. Okay, so that's what cosecant looks like. Now notice, so how long does it take to repeat itself? Switch colors here. So that means I need a down and an up. So if I go from negative pi, I have to go all the way to pi in order to get both. So that has length 2 pi. Okay, so that's going to be the period here. So the domain, we can't have x being multiples of pi because those are where sine is 0. Okay, the denominator. Now the range is a bit weird. So notice, so forget that this green graph. Okay, so remember that green graph doesn't actually, it's not there. We're only looking at the blue graph. So for the blue graph, I can get all y values that are 1 or bigger, and all y values that are 1 or -1 or smaller. But I cannot get anything in between 1 and -1. So the range here is negative infinity to -1, including -1, and then 1 to infinity, also including the number 1. Okay, so maybe I'll just write here. We cannot get any y values where the y value is between 1 and -1. Okay, so those are the ones we cannot get. We can get all the others. Okay, the vertical asymptotes are all the points that are not in the domain. Okay, so those are going to be at multiples of pi, integer multiples of pi. Okay, the y-intercept, so we actually don't have one because we never, that's a vertical asymptote, so we never cross that. Okay, so there's no y-intercept. Okay, there's also no x-intercept because we never have y equals 0. Okay, so there's also no x-intercept. Okay, now cosecant again is an odd function, so it's symmetric with respect to the origin. So that's because sine is an odd function. So cosecant of -x is 1 over sine of -x. And sine is an odd function, so sine of -x is negative sine of x. So that's -1 over sine x, which is negative cosecant x. So that's how we know that it's odd. Now the period for cosecant is the same as for sine, so it is 2 pi. So the graph repeats itself every interval of length 2 pi. Okay, so that's how you get one full cycle if you take an interval of length 2 pi. So you have to get, so it looks like it could just be pi, right? But you have to get the one that's up and the one that's down. So that's why you have to do 2 pi. So that's what the graph of cosecant looks like. Secant is very similar. Okay, so try that same method to try and get the graph of secant.